Okay. Oh, is that right? Okay. I missed that one. Good. Thanks for letting me know. All right. So my goal today is just to finish up some discussion items for the hydrogen atom. We've done the tough derivation part of it. And now we're left to sort of think about and make sense of the kind of monstrous formulas that we have. But I also said you could bring in your Dirac notation homework problems that you're supposed to be working on were nominally due yesterday, just so that if we have extra time, once we finish talking about the hydrogen atom, maybe an extra 15 minutes or so, we can finish up the details on that. I mean, I feel like it was a very busy week, but people are starting to lag behind on the homework, which isn't a problem for me, but we don't want to continue to get further and further behind. Otherwise, that will be disastrous. I also looked, normally I'm going through section 5.2. Now, these last sections are pretty beefy sections. So we are going to spend quite a long time on 4.3 and 4.4 and 5.1. But, we still have, a number of weeks left. So I think we have time to kind of slow down, mellow out a little bit, and just make sure that we're catching up to where the things we've been talking about. So let's just see where we end up here. So we did the derivation for the hydrogen atom, and we found out, you remember the whole thing was, we already knew the angular part. That's these spherical harmonics, which are the, polynomials in theta times e to the I m phi. And then the whole point of yesterday was to find the radial wave functions, which here I've got expressed as a function of rho. Remember, rho is proportional to r. So, and the constant of proportionality was kappa there. So this is almost written as a function of r. This was our u of r, and then we have to divide by r to get capital R of r. So that's what we're after. So this is the whole wave function. It depended on three quantum numbers, n, l, and m. You can't see the n in here right now, but there's a different one of these polynomials that appear right here for each particular value of n and l. So this depends on what your n and l quantum numbers are. Okay, so that, and I think where we stopped last time was saying this v of rho, again, we did a series solution, but we found out we were going to be in trouble unless we had the series terminate. So they're actually polynomials, and they're called the associated Laguerre polynomials, and they depend on n and l. It would be nice if you had n as the subscript and l as the superscript, but someone in mathematical physics made up the subscripts and superscripts before we knew about quantum mechanics, and so the n that we define and the l we define are related to the superscript and subscript this way, but you don't really need to know these. I mean, that's not something that you're ever going to have to decode. That's just the conventional way to express the superscript and subscript in terms of n and l. Okay, they're functions of rho. Here's what they look like. Unlike the other polynomials we were looking at, say like the Hermite polynomials, which were either all even powers or all odd powers, these have to have every power of x, because remember, the way we made them terminate was once one power of x had a zero coefficient, all the ones after it have zero coefficients. So they can't be, these particular polynomials can't be missing any powers. Once you start with a constant, if you've got a first, if you have a constant, then it's either ends there or you've got to have a first power of x, and then you got to have a second power of x, but you can't skip any powers of x. So they're polynomials, but with no missing powers of x in them. So they're part of the radial wave function, and I'm going to show you from Griffiths the full table of normalized radial wave functions in just a second. But you see, they're functions of rho. Rho is kappa r. It's more convenient to express kappa in terms of what's called the Bohr radius, A. And you can just think of that right now as just a constant. So the Bohr radius combines a bunch of these kind of constants that are appearing everywhere. The 4 pi, epsilon 0, h bar squared over me squared. Those are all defined to be the Bohr radius. you could just check that it has dimensions of distance, and then it would make sense to call it some kind of radius. So in any case, these are expressed in terms of ratios R over A that appears in here. Okay, so when we write down the radial wave functions, they depend on both n and L. So we conventionally put the n subscript first and the L subscript second. And you see, we had rho to a power. So here's a rho to the 1. We have a polynomial in rho, which is proportional to R over A. And then we have something that makes it eventually go to 0 pretty quickly as radius increases. So something's wiggling around, but this eventually makes it go to 0. So it wiggles a little bit. This is a linear polynomial that doesn't do much wiggling. Here's a quadratic polynomial that wiggles a little bit more. As you go to higher and higher ends, you can get higher and higher degree polynomials. Okay, here's the picture from Griffiths of these polynomials, and they don't look too much different than the kinds of things we saw for the spherical square well, except they never go to 0, right? Spherical square well, they just were forced to go to 0 at some radius where your spherical region ended. Here, they're doing things like they wiggle a little bit, and then that exponential function forces them to exponentially go to 0 as R goes to infinity. Now, you might be surprised that the energy here just depends on that quantum number n. We're going to find out later on that this quantum number script L tells us about the total angular momentum. And you probably know that usage from modern physics, right? And you would think the more angular momentum something has, that's kind of like kinetic energy, right? If I have something with a lot of angular momentum, I have a lot of kinetic energy. And so superficially, you might think, well, why doesn't the energy depend on the total angular momentum? Because it should, right? The faster you're spinning, the more energy you have. Well, it's sort of a trick, or it looks like it doesn't, but look, the definition of n has L in it. So as you change L, you're changing n. So this really actually does have some L dependence in it. And for example, it would have been a reasonable definition to say, instead of taking our quantum numbers to be n, L, and m, we could have taken our quantum numbers to be J max, L, and m. And then the energy would have depended on J max and L, just kind of like it did something similar for this spherical square well. But it sort of simplifies the energy formula to have it only depend on one quantum number. So you can't really tell, just by knowing that what n is, you don't necessarily know straight off the bat what L is, or vice versa. Let's just compare these graphs to a couple of these. So I selected some things from Griffiths' table. For example, let's see, what's one that's easy to see? 3, 1 is this solid curve that starts out at 0, goes up, crosses the axis, and then it looks like it's heading exponentially to 0. Let's just check that that makes sense with this formula here. We've got a factor of R over A. So that's going to go to 0 when R goes to 0, right? Because I have an overall factor of R. When R goes to 0, this whole thing's going to be zeroed out. Sure enough, when R goes to 0, it's heading down to 0. Notice that R30, that's this solid curve that's going up to here. It doesn't go to 0. Well, there's no overall factor of a power of R over A. So it looks like as R goes to 0, this thing in parentheses is going to 1, right? So that kind of makes sense there. So again, going back to the 3, 1, 1, it's 0 at the origin. That's due to this factor. And then where else is it 0? Well, there's also a linear factor here, which is going to have a 0 at some non-zero value of R, right? And so we see, oh yeah, there's another 0 of that function where it crosses the axis there. And then eventually it's going exponentially to 0. That's due to this factor there. If we had a quadratic polynomial out in front plus a factor there, I might expect 2 zeros. And so in this case, where there's a quadratic polynomial, I generically expect 2 zeros to that function. Now, if you look at the 3, 0, 1 on here, you see it crosses down. There's 1 0 there. There's a second 0 there. So it's crossed twice. That's due to that quadratic polynomial, which has 2 zeros to it. And then it starts exponentially going to 0. So, you know, if you really look into these functions, you can find out a lot and match them up with those radial wave functions. Okay. Griffiths puts it all, you know, without any explanation of where this normalization constant comes from, in this grand form here, where we've got the radial wave functions, we got the angular wave functions, and we got a normalization constant there. Here's just a voting question. This doesn't necessarily go in right here very well, but it's a good thing to ask. So we're talking about the angular dependence here. I'm not talking about the radial dependence at all. So let's suppose the quantum number little m is large. What can we say, what can we conclude about the wave function and probability density as we vary just that azimuthal angle phi spinning around the z-axis? Okay, so we're supposed to answer about what happens to the wave function as we go around. That means this, just this. What happens to the probability density, which means the magnitude squared of this part of the function? We're ignoring the radial part because we're just concerned with how it changes as you go around in phi, not as you go to different radii. So take a second to think about that. All right, if you got a vote, hold it up. Try to look at Alvis 2 on the screen. Okay, I'm seeing 3 people definitely voting. 2 of them are voting for C, rapidly varies, no variation. That's actually the correct answer. Would one of you, both of you are in the room here, would you like to explain how you're thinking about that? Yes, so Yi-Chen is saying the probability density is the magnitude squared of the wave function. We're given the relevant part of the wave function here. So yes, when we take the magnitude squared of the wave function, all the phi dependence goes away. And that is always true, no matter which state you're in, doesn't matter what n, l, and m are. There's never any phi dependence of the probability density. Okay, it's always constant as you move around in phi. Okay, and then why is the wave function rapidly varying? Right, we're told that m is some large integer, and therefore as phi moves around, you know, it's going around through that corkscrew motion really quickly. The bigger m is, the more quickly it corkscrews around as you move around in the phi direction. Okay, that's just, I'm trying to force you to kind of decode all these things because there's just so many symbols when you look at this. It can be kind of confusing. Uh-oh. Screen sharing is paused. That's weird. Okay. Resume share. Lost contact with my clicker. Okay. That kind of explains why, you know, everybody's seen these pictures before, I hope, of the hydrogen wave function probability densities as a function of position. Of course, r equals 0 is at the center of each of these. The triplet of numbers here give n, l, and m, and we tend to put them always in that order. So n, the one that determines the energy, then little l, then little m last here. And the reason we can get away with 2 dimensions is that we just discussed how the probability density doesn't depend on the angle phi. So you can imagine each one of these diagrams, we could spin it around that central vertical axis and it would, just trace it through space. And so it's going to have sort of circular symmetry in the phi direction for all of these. So, even though this looks superficially a lot like this one here, just rotated, they're actually showing quite different probability densities, right? This one is kind of like 2 bulb-shaped things, right? One up at positive z and one at negative z. They're kind of like spear-shaped kind of bulbs, right? Whereas this one is a donut. If I rotate it around in the phi direction and let it sweep out its shape, I've got those sort of almost circular cross sections going around like that. So there's a little bit of mental interpretation that has to go on with these. But you can generically see that, well, first of all, when L is 0, and when L is 0, of course, M has to be 0 because M can only go from minus L to L, we get spherically symmetric kinds of states. So here's 2, 0, 0, 3, 0, 0, that's L equals 0, 4, 0, 0. They are, as you rotate them around, they have spherical symmetry. Whereas when L is non-zero, then you start to get dependence on theta. Theta changing as you go from the top to the bottom. Theta is going from 0 to pi. Okay, so furthermore, with this normalization, these states are all mutually orthonormal. And again, we have to be careful because we're in spherical coordinates. That means the integral of psi star with a certain NLM index times psi with an N prime, L prime, M prime index, that's an inner product. We got to put it next to the spherical volume element. But when we do that, and we integrate over all space, we get something that is 1 if n equals n prime, and if L equals L prime, and M equals M prime, but 0 in all other cases. So they're mutually orthonormal, normalized and orthogonal to each other. Okay, let's look at the worksheet that we've been chipping away at. It's the one with the staple in it that we used yesterday, and can't remember if we started it the day before, but we were at least using it yesterday. It says hydrogen in the upper corner. And we're now, I think on your version of the worksheet, this is listed as problem number 6. It doesn't necessarily have to do with normalization, but it sort of tells us, well, we'll find out what the message is. So it says, recall the energy eigenstate for the ground state of hydrogen. This is n equals 1, L equals 0, M equals 0, right? The explicit form is there and it's normalized. The Bohr radius value is given there, but it's written in terms of A, right? It's e to the minus r over A in the function. What's the most probable value of r in this state? In other words, well, first of all, it's L equals 0 state, so that means it's spherically symmetric. So it shouldn't depend on what angle you're at or anything like that. As you're moving out in R, you're moving through that spherically symmetric kind of probability density. Where is the probability density largest? In other words, in what region of R are you most likely, for what small range of radii are you most likely to find the electron in a hydrogen atom? Here's a hint. Let me just unshare my screen for the sake of the video. You can't just look at the magnitude of psi squared, because the probability interpretation is that if I take the magnitude of psi squared, here I'm using lowercase psi because it's in a definite energy state, so it's one of those definite energy states. Here we're talking about the state 1, 0, 0, times the spherical volume element. This is the, this is what I would call rho of, well, in any case, if I integrate over some region of this quantity, I get the probability of finding an electron in that region. Now, if I just want the probability of finding an electron as a function of r, in other words, if I want to find rho just as a function of r, but I don't care about theta and phi, one possibility is I could integrate this thing over theta and phi only, but leave the r dependence in there, and then that would give me rho of r dr. Okay, so if I calculate the integral from phi equals 0 to 2 pi, I don't really care about the phi dependence, and the integral from theta equals 0 to pi, all phis and all thetas, then what I'm going to be left with is rightly interpreted as the probability density as a function of r times dr. And the kind of trick aspect of it is it also is going to include this r squared in it, right? I don't just care about the form of this, but I need to include that r squared in it in order to think about it, right? So I'm saying I don't really care about the probability in all the other directions. Let's just add it all up. But I really do care about how it varies as you change r. So let's not integrate over r. And then let's find out where this resulting function is a maximum. That means take the derivative and set it equal to 0, right? Good old calculus 1 techniques. So see if you can figure out what rho of r is, take the derivative and set it equal to 0, and see what value you get in terms of the Bohr radius. Incidentally, do you guys, have memorized from it happening so many times that when you integrate sine theta, d theta, d phi over all thetas and phis, what number do you get? 4 pi, right? So that's something you can just write down. I mean, you could do it and evaluate between the limits, but the integral from phi equals 0 to 2 pi, integral from theta equals 0 to pi of sine theta, just the angular part of the spherical volume element, that adds up to 4 pi. I mean, they're easy integrals to do, but you don't want to, it comes up so often in physics, it's just kind of nice to remember that and not do, let's see, derivative of the cosine is minus the sine, so the antiderivative sine is minus cosine, I got to evaluate between it. It's just more, anytime you have to do more work like that, it's a barrier to thinking deeply into a problem because you're lost in the weeds, and it's sort of nice to just remember facts like that. People say there are 4 pi steradians in a sphere. That's what that 4 pi represents. When you integrate over theta and phi, you get 4 pi. Okay, let's follow the logic through here. The answer is actually A if you finished it. So the most probable radius is the Bohr radius. So, you know, it deserves some degree of fame for that. Or it's a nice handy interpretation of it. Okay, so I said when you integrate over these angles, you get a factor of 4 pi. And then the stuff that's left is the magnitude. So anything that's a constant, I'm just going to put as a constant out in front, because what I'm trying to find when something is a peak, I don't care about a constant that's multiplying out in front, right? That's not going to affect the location at which the peak occurs. So I've got a 4 pi that appears in there. For the magnitude of psi squared, I have to look at the statement of the problem, and it was a constant. Psi was a constant times e to the minus r over a, so that means the magnitude of psi squared is e to the minus 2r over a, plus some extra constants, which I'm throwing in there. And the only other thing I'm left with here is the r squared and dr, right? Okay, so it looks like up to a constant, this is the important part of my rho of r. Rho of r is at least proportional to that thing there. And I want to find out where it is maximal. So let's take the as a step towards that. Let's take the derivative of rho with respect to r. I've got a product rule. So I have derivative of this one times that exponential function plus r squared times the derivative of the exponential function, which gives me a minus 2 over a times e to the minus 2r over a. And then let me try to factor out all the common things here. I've got a factor of 2, a factor of r, and I've got the factor of the exponential. So let me factor that out of the entire thing. Tell me if you see me making any mistakes. Times, if I factor out an r, this whole thing is here, so I get a 1 plus, and, sorry, I've got a minus there. And then I've got another factor of r over a. And I think that's it, right? So we're going to take the derivative, set it equal to 0. Okay, I've got a product of a bunch of things equaling 0. One of them's got to be 0, right? 2 is never 0, so don't worry about that. R is only 0 at r equals 0. So I would say either r equals 0, or where's this 0? Nowhere, because we're talking about r has to be positive, right? Well, in any case, exponential functions are never 0, right? They never cross the axis. It only gets closer and closer, but never crosses it. So this can't be 0. And this is 0 at r equals a. Right? If I set that thing equal to 0 in parentheses, I get r equals a. And then the only question is, well, okay, which of these are maxima and which of these are minima? So I can look at my, original function right here, which is giving me rho of r, and I can say, well, look, what's the basic shape of that function? Here's r equals 0 as a function of r. This is forcing it to be 0 and start going up like this until this function then forces it back down again. So r equals 0 is actually a minimum, a local minimum, whereas r equals a is the local maximum in the probability density. So this is the one we're actually looking for as a maximum. That's an interesting factoid, that you're most likely to find a ground state hydrogen electron at a distance a away from the proton. Yeah.
Are we still able to understand it as orbiting? I was obviously not fixed orbit, but how we understand? Is there a way to understand how the electron moves? I know this is showing where it's most probable, but
yeah.
help us explain its movement.
Well, no, we don't think of it as moving in the conventional sense in the same way that, if I have the infinite square well in one dimension, right? And I would say, we've got an electron in an infinite square well between 0 and A, just on the x-axis, right? And we say, okay, it's in the ground state. Looks like that, right? Some sine kind of function. How is the electron moving? Yeah, it's like when there's a wave, it's not moving. Now, that doesn't mean that if I make different measurements, I might get a variety of values, right? If I measure position, if I set up 1,000 identical electrons in this state, and I measure it 1,000 times, I'm going to get relatively more position measurements in the middle than I will towards the ends. And that's something you can experimentally verify. But we don't think of the electron as moving at all. The only case where you can think of it as moving is, in the case where you put it in a state that more or less, there's always going to be some uncertainty, kind of the same way that's here. Here, there's no motion at all because it's a stationary state. But I might, in the harmonic oscillator kind of state, I could put it in a state where it's very narrowly peaked around a certain x, and it actually, but it's not so narrowly peaked that it just zooms everywhere really quickly, because the smaller my x uncertainty is, the larger the momentum uncertainty. If I make it too narrowly peaked, it's just going to zoom apart and look like chaos. But if I make it just narrow enough so that it looks like it has more or less a definite position, more or less, and the momentum spread isn't too wide, you can actually follow it along and see that that probability sloshes back and forth in the harmonic oscillator potential. And I think we looked at that in one of those simulations. So that's kind of like trying to connect it with classical physics, at least in the best sense that you can. But here in this particular state, this is a stationary state, so there's no motion at all. And it wouldn't correspond especially well to an electron moving in this case, right? Because if you think of the only case where an electron moves, right, it's sort of like I got a proton here. The electron, if I wanted to imagine it doing it, would be some sort of solar system model, right? But this state is completely spherically symmetric. Whereas solar system kind of movement isn't spherically symmetric. It's got a definite plane of motion. It would be different than if it were going around in this direction. Whereas this state is actually the same all the way around at all angles. So there's nothing really analogous to it in terms of classical motion. Okay, share screen. Let's see what else we have here. There's some discussion, I think, in the book of the spectrum of hydrogen, or at least in my notes. I can't remember what was said in the book. And the thing that's somewhat confusing, and I guess the reason I wanted to mention this is because, the first thing you learn in modern physics when you're studying the Bohr model is that, well, how do we know about all these weird energy levels? It's because we look at the energy of a photon that's emitted when it makes a transition between, you have some hydrogen and you send a current through it, or you heat it up in a certain way that causes all these levels to be populated. And as the electrons go down, they emit characteristic wavelength radiation. Now, you're not going to see this in our non-relativistic quantum mechanical model of hydrogen. There's nothing like that spectrum that's appearing here, because first of all, if an electron starts out truly in an n=3 state, it's there forevermore. That's a stationary state. So it's never going to jump down to the ground state. There's just no mechanism for that in our model. Now, in the real world, or the more real model of quantum electrodynamics, we know electrons couple to photons, and you can have an electron change in energy level and emit a photon that has the same energy that corresponds to the loss in energy of the electron, and momentum is conserved and all that kind of stuff. But we just don't have any description of photons in our model, right? They're relativistic particles. We're doing non-relativistic quantum mechanics. So in this case, you're going to see those energy eigenstates. Normally if you put an electron in an n=3 state, eventually, probably sooner rather than later, it's going to jump down to the ground state, most likely, or at least a lower energy state, and then end up in the ground state. But for us, we can sort of think of, well, You know, as long as you're not waiting too terribly long, these stationary states are just approximately stationary states, but eventually it's going to couple to a photon. We don't have that description in this particular theory, so we don't have a mechanism for thinking about it. But nonetheless, we have correctly found all of the values of these energy levels. That's given by our formula for En, which is minus 13.6 eV over n squared. And you solve the stuff in modern physics of the various series, depending on where you start and where you end. The Bohr energy formula, which is essentially the one we just found, minus 13.6 eV times 1 over n squared, tells us what the energy differences are. And if you then use the Planck formula that tells us as a function of energy, how does energy relate to the wavelength of a photon, we can convert that into the wavelengths of the photon, and you get what's called the Rydberg equation with the Rydberg constant in there. Rydberg didn't know that the constant was equal to all these things, but now we know in our theory this is how to write out, fundamentally speaking, what the Rydberg constant is. So this comes from the Bohr model. Okay. And the visible, as you may remember, the visible lines of hydrogen all land on n equals 2. These ones that land down here on n equals 1, that's a big energy difference. That means they're in the ultraviolet, so you can't see them with your eye. And these ones up here, the Paschen series, right? The Lyman series is the one that ends on n equals 1. Those are all in the UV. Paschen series and the ones that are higher up are all in the infrared, so we can't see them with our eye. But Balmer, Johann Balmer, everybody likes to say he was a school teacher. I guess he taught some like elementary school or something, but he had this hobby of looking at visible spectrum. He observed the hydrogen emission spectrum and actually fit a function to it. So he was the first one to sort of see the pattern here. It looks like there's an obvious pattern of, you know, spacing in wavelengths sort of varying regularly until you run out of visible, but it seems like if you kept going, they might get closer and closer together. So he fit a pattern to that. And then after, you know, better invention of apparatus that could observe infrared and ultraviolet radiation, Rydberg was able to string them all together and say, look, all of these lines fit this formula, right? Where you have these two integers, the integer of the starting and the ending state, and my formula tells you what the wavelength is going to be. Still not a fundamental theory. That was before the Bohr theory, which nobody thinks of as a fundamental theory, but it sort of was a conceptual basis to pull all that together. Okay, here is, I decided I don't want to do, you can look at, I'll post the solution to the last one that's on that long worksheet we've been working on, but instead let's just do a last worksheet problem to try to decode these probability densities and sort of compare them to all these, you know, mind-boggling formulae you see in Griffiths. So here, I've chosen one from that picture. I'm not going to tell you which one, but I want to be able to look at this probability density plot. Plus z is up here, just like usual. What do we know about the quantum numbers n, l, and m for this energy eigenstate whose probability density is being shown here? And so I'm first going to show you this table from Griffiths of the R radial wave functions. You have to remember the subscripts are n and l for the R wave functions. And by staring at that, how can I figure out, or at least restrict somewhat, what the possibilities are for n and l? Yeah, we can look at where it goes to 0. And in fact, you know, these are only telling me what happens in the radial direction. So forget for the moment about what's happening in the theta direction. We're not seeing that in this table. I'll show you another table which helps us with that. So in the radial direction, what do you see? Where are the zeros? Or how many zeros are? Is there a 0 at r equals 0?
Yep.
Yes. You know, dark here is low probability. That's the context of that particular way of displaying it. So there's a 0 at r equals 0. There's another 0, it looks like, at some finite distance. And then, if you believe that nothing else important happens after this, it seems like, well, it doesn't reach 0, but it's exponentially going to 0. So that last part getting dark, we could probably attribute to this exponential function, which is damping it down close to 0 as you go away. So what we found out is that there's 1 0 in between r equals 0 and infinity. So in the ones that are shown in the table here, what R and Ls are going to be consistent with that? Let me just, to start with the random one, let's just look at R30. Can anybody figure out why R30 cannot be pictured there? Say that again. Yeah, so it looks like a quadratic, at least, generically a quadratic function has 2 zeros. But even more importantly, what's going on at r equals 0 in this equation? Is this factor 0 at r equals 0? No, exponential is going up to a constant at r equals 0. Is this 0 at r equals 0, this polynomial here? No, when r equals 0, it goes to 1. And then I've got another constant. So it's definitely non-zero at r equals 0. And it looks like it's going to 0 there. So it can't be this one. This one goes to a constant. Now this one here does go to 0 because it has a factor of r over a. So when r goes to 0, this factor forces it to 0. This one also has a 0 at r equals 0. Right? Can you help me distinguish between these two, R31 and R32? They both have zeros at the origin at r equals 0. But which one predicts exactly 1, 0, and then it heading to 0 as you go off to infinity? 1, 0 at a finite r. Maybe you're missing it. This is an R31. I don't think R21 does that. It only has the 0 at the origin, and then it heads to 0 as you go off to infinity. So it would be missing this one at a finite r. But R31 does have it, right? Because this forces it to 0 at 0. This forces it to 0 as you head off to infinity. But this has a 0 at exactly 1, 0 at a finite r. R equals 6a. So that looks like it could be, this could be at r equals 6a. I don't know, there's no scale on there, so it's hard to know. So maybe R31 is a possibility. What about down here in the n equals 4 selection? Which one of those 4 seems like it's consistent with a 0 at the origin and then only one more 0 at a finite r? 4, 2, right? 4, 2 looks like it's got that linear factor that we're looking for, right? This one has a quadratic factor, so I would expect 2 finite radius zeros. This one I only expect 1. This one has 0 of them, only the one at the origin. And this one doesn't have one at the origin. So we can restrict it to, let's see. Oh, I also put R20 on here. Now, you need to tell me why I can throw away R20. This one has a linear factor in there, but what's it missing? Yeah, it's missing r equals 0. It's missing a factor of just plain old factor of r or r squared or something like that. So that one I'm going to throw away. So the ones we've picked out here are 3, 1 or 4, 2. If the table were more complete, you'd see 5, 3 or 6, 4, right? There, the m has to be, the L has to be 2 bigger than the n. Okay. So there's my list of possibilities that I have so far. Now let's go to the YLM. And remember, the YLM is an e to the IM phi times a PLM. So the important stuff, we're seeing the theta dependence. It's all in the PLM stuff here. So I'm showing the table of the theta dependence only. I left out the phi dependence just to make it simpler to look at. And remember, the subscript is L, superscript is M when we write YLM or PLM in this case. All right, so now looking at the theta dependence, ignoring the radial dependence, which ones in the table look like they might be possibilities? Or just to put it a different way, why is P10 not a possibility? Yeah, I mean, it's got a 0 at theta equals pi over 2, which certainly looks like it works, but it doesn't have one at 0 or pi. So, sorry, what was that? P2, oh yeah, we always read the subscript first. So 3, 2, just because we always do the L before the M. So this would be P3, 2 has a 0 at theta equals 0 and theta equals pi by virtue of the signs, and 1 at pi over 2 by virtue of the cosine. That's right, so 0 here and at pi over 2 and at pi. So that's consistent with this one. What else? P21 is also there. So those are our possibilities. And that means, again, remembering that the subscript is L. L equals 2 as a possibility. Our only possibility here from our first bit of information was the second row. So that would make that a 1. And if L is 3, then M has to be 2. So that tells us something about those. And also, I guess this one wasn't in the list, right? L equals 1. If you look at the L equals 1 possibilities, none of them have the right zeros as a function of theta. So that's out, and we can put in those other numbers for M looking in there. Right? So we can't narrow it down precisely, but we can get a very narrow list. And if somebody said, well, it's 4 or below, then n equals 4 or below, then you would know that it's this one. So I'm just trying to force you to kind of look at this and see, God, these tables look really mind-numbing, but you can see all the features that are in there as n and L get larger, or sorry, as n and L get larger, especially when n gets larger, you get a lot more zeros along the radial direction. And as L and M get larger, you tend to have a lot more zeros along the theta direction. And they're always symmetric with respect to phi. So that's why we don't display that kind of stuff. Is this my last slide since nothing's happening here? No. One more question I wanted to ask here. And that is, well, here's something that just kind of occurred to me at one point. Okay, we've got our probability density functions. We've got our energies that just depend on the quantum number n. And I've got the quantum numbers listed down there. They're kind of small. Oh, and by the way, where's the one I chose? Here it is, 421. So it actually was 421. I took it from this table, which only goes up to the 4s, it looks like. Let's imagine 2 different initial states that aren't energy eigenstates. And I'm going to show you what their probability densities are. Maybe they're, so I'm imagining it's 2 blobs, kind of like a 3D figure 8, right? Blob up, snowball up here, snowball down there, right? And so I might say, well, here's one way to have it at time t equals 0. High probability at positive z, high probability at negative z, and 0 in the middle. Now I could take this whole thing, these 2 blobs, the 2 snowballs, and just rotate them so they're lined up on the y-axis instead of the z-axis or something like that, right? So I don't mean that this is a donut shape. It's not symmetric as you go around in phi. It's still 2 blobs. It's the same exact function. It's just rotated in space. Now, when you rotate an initial state in space, it shouldn't change the energy of it, right? Now, the energy only depends on n. And yet, so when I take a state like this, or a state like this, or indeed some other state where it's, again, 2 blobs here, but they're at a different angle. When I change between these 2, clearly I've got to have a different linear combination of these definite energy states, so that when I expand each of these 3 states, which correspond to just 2 snowball-shaped blobs in space, just oriented different ways, these coefficients that are out in front, when I expand it as a linear combination of definite energy states, those coefficients have to change. It's going to be a different linear combination of those definite energy states. even though the state itself is just the same. Now, what I wanted to address is, well, how much can these change? Clearly, however much probability is in a certain n value collection, that same amount of probability has got to stay within that n collection, right? Because the energy depends on n. So however much probability I have to be in the n equals 2 state, corresponding to these kinds of states, it can't change as I go from this one to this one to this one, because they've all clearly got the same energy. All they are just oriented different ways in space, which means that as I reorient either which way my z-axis points, or I reorient my initial state in space and keep z-axis the same, the probabilities associated with the same n value are going to sort of exchange within each other, but you're never going to have more probability end up in n equals 3 and less in n equals 2 when you do that. And actually, the same thing is true with the L value, so that when you just rotate a wave function in space, we'll find that the probabilities associated with all these different states do get mixed together, but they only get mixed between the m's, with the n and l stayed the same. So the expansion changes, but the probabilities associated only with the m's change. And I wanted to kind of show you a simulation. I guess I spent longer than I thought I was going to today doing this. Here's my favorite website. This is showing quantum mechanical wave functions. Let me switch to the form I want. So this is, right here, if I wanted to put it in the ground state, that's n equals 1, for which the only, whoops, I guess I got to clear it out first. Just put it in the ground state, hey, nice and spherically symmetric. If I put it in one of the first excited states that corresponds to L equals 0, it looks like this, still spherically symmetric. Right? I could rotate this and nothing changes as I rotate the orientation of those. Let me try to get it back so Z is up. Now I've messed it up. That's not good. Trying to get Z to go straight up. If I put it in, so this is n equals 2, L equals 0. Sorry, n equals 2, L equals 1, and m equals 0. Let me just show you something back on here. What I was going to say is, if it's in this state, it seems like it would have a lot of this in it, right? If I were going to say, I'm going to write this as a linear combination of all these things, it seems like the coefficient in front of this would be pretty big. Whereas if I start out with this state, which is just trivially rotated with respect to the first one, it doesn't seem like there would be a lot of this state in it. And remember, this one's shaped like a donut, so it's not necessarily true that there's a lot of this one in it. But it's got to be some different linear combination of those. So if I go back to, let's see, where is it? Here we go. This is n equals 2, L equals 1, m equals 0. If I go to m equals 2, L equals 1, m equals 1, instead of being vertically separated, it's more or less horizontally separated. If I take a linear combination of the n equals 2, L equals 1, m equals 0 and 1, let me try to take a linear combination of those. You get something that can be rotated at a certain angle, tilted with respect to the axis. So the point I wanted to make was, as you take an initial wave function, you just rotate it in space, or you just say, I'm going to change the direction that I'm going to call plus z. Then exactly how it is a linear combination of those definite energy states changes, because they obviously have an orientation with respect to plus z. But the change that's going to happen in those expansion coefficients is all the probability that's in a particular n and L sector just gets shifted around between the m's associated with that n and L, right? Because all I'm doing is switching the z-axis in there. I don't know if that had the punchline I wanted it to, but But it was sort of confusing to me. I remember the first time when I was looking at this thinking, well, wait a minute, it's sort of a trivial change when you go from here to here, but this expansion has got to totally change because there's a definite kind of vertical orientation that I can see in all of these. And if I tilt it to 45 degrees, it's obviously got to be a totally different linear combination of all those. And it is totally different, but not completely randomly different. The probabilities sort of stay within little sectors and just get juggled between different m values for the same n and l.